So yeah, today I'm going to show you, or start off on our journey to cool, complicated models that you're not really expected to wholly, uh, I guess, learn about or sort of become one with. Um, more to pique your interest in cool stuff that you can do. Again, still using all the tools we've used so far, um, and get you thinking about down the road maybe learning them for use in your own research. So we've been talking in the last little bit about hierarchical models, um, and how they've become. I mean, I guess I haven't told you how, but that I will outright states that they've become somewhat sexy in psychology in the last 10 years, I'd say, because we often have hierarchical data that we've in the past typically simply averaged out measurement and tried to average out measurement noise and then work from there. But there are benefits to actually letting your model see the measurement noise. For example, when that measurement noise is confounded with another variable, like we had with the last set of models where word sort of introduced its own variability to the outcome. But there's all sorts of uses to which you can put hierarchical models, and one of them I'm going to show today. So the example I have today, it comes from a scenario, well, maybe I'll even sort of simplify it a little bit. Let's say for each person, they're measured in each of condition for A, so there's A1 and A2. This is going to be an experiment where we have somebody playing a simple video game, and they have to identify, say, whenever there's a square on the screen, press one button. Whenever there's a diamond on the screen, press another button. Incredibly boring experiment. Usually, if we were actually doing that sort of thing, we'd have a whole bunch of manipulations. Here, I'll simplify it down so that there's two conditions under which they're responding, A1 and A2. So in each condition, we can measure their reaction time, but we can also measure something like, again, in both A1 and in A2, their error rate. So for each response, they have a reaction time. They also have whether they got it right or not. So you've got kind of bivariate data in this scenario, where one you might assume a Gaussian distribution for error, and another is just a binomial thing. It's 1 or 0 for each outcome. So for a given person, you can say, okay, you can take their collection of RTs in A1 and say, what is their mean RT in A1? Collection of RTs in A2, what is their mean RT in A2? For error rate, well, I've already shown you how to, within a group, translate, say we had a bunch of ones for a group called A1, ones and zeros for a group called A1, and ones and zeros for a group called A2. And so you can translate that onto the log odds scale, and you'd have, again, error rate on log odd scale for A1 and error rate for log odd scale and A2, and that allows you to then talk about the intercept and effect. If that were two groups, you can do the same thing if it's within a person. Again, you just say that that person has an intercept and that person has an effect for error rate on log odds, still feeding in binomial data, ones and zeros. And ditto up here, you can talk about this person having an intercept for their overall mean RT and a effect relating the difference between these two conditions in RT. So let's actually put for RT and the effect of that on RT. And we can talk about the intercept for error rate and the effect for error rate. Now, I've already given you the tools to do this analysis all by itself when you have a bunch of people. So this is the hierarchical Gaussian models that we've done. I've given you tools to talk about this analysis all by itself. That's the hierarchical binomial data that we've already done. But what do you do if you have the data that's bivariate like this? You've got two outcomes. Well, you could just do two separate analyses. But that can be, in some scenarios, less powerful than what I'm going to suggest you do, which is to do a single model that is trying to estimate all of these things together. Now remember, within each independent model, we actually have an intercept for RT, an effect for RT, and then sort of let me actually even start this on a different piece of paper. If we were just doing the RT model, we'd have the idea that there's a distribution of intercepts for RT. So that distribution would have a mean for the intercept for RT and some variability. I'll call it actually S, some standard deviation for the intercept for RT. And ditto, we'd have a distribution across people of effects on RT. So we'd have a mean for the effect on RT and standard deviation for the effect on RT. Because again, we can compute for each person an intercept and each person an effect. So there's some distribution across people and that will characterize as just normal. So whenever we have a situation like that where we have variability across people in one parameter and variability across people in the other parameter, we can also have a correlation. I'll just call it R because that's what you're probably familiar with. So correlation between the intercept for RT and the effect for RT. All right, well, so let me start making a list of parameters. So we've got the mean for the intercept for RT, mean for the effect for RT. If you imagine, well, I'll just continue. Standard deviation for the intercept for RT, the standard deviation for the intercept, or sorry, for the effect for RT, and a correlation between intercept for RT and the effect for RT. So that's if we just did the RT model. If we just do the binomial model, we have all these same parameters, but wherever you see RT here, change it to error rate. So we can even just start adding those. So we've got the mean for the intercept for error rate, and mean for the effect on error rate, and mean, or S for the intercept on error rate, and S for the effect on error rate, and we'll add in R, the correlation between the intercept on error rate and the effect on error rate. All right. Well, if we model these two things together, then we still have all these means and standard deviations, but we then have the ability to additionally capture any correlations across the different measures. So you would have a correlation between intercept for RT and intercept for error rate. And ditto, a correlation between the effect on RT and the effect on error rate. And finally, a couple more, correlation for intercept on RT, the effect on error rate, and correlation between the effect on RT and the intercept on error rate. Is that everything? Yes.
Should be 6, right?
Yeah. So we can estimate a number of other relationships in the data. And in fact, to the degree that there are these relationships in the data, we'll improve our precision of analysis on everything else. So by combining these two variables together to the degree that there's relationships hidden in the data amongst those variables, we actually improve our statistical power. Now, it's a much larger model because we now have many more variables and relationships to account for, so it's going to take more time to compute things. But time, you just run things overnight if they get excessively large. So I'm going to complicate things just a little bit by telling you a little bit more about reaction time data. Well, actually, I already told you a little bit about this, so let's go back to the reaction time plot that I just had, RT in A1 and A2. If you recall, when talking about hierarchical Gaussian models, we not only have to talk about the intercept and effect for each person, but we have to choose some sort of way to parameterize the fact that there's noise within a person. So that's that measurement noise thing that I previously signified by the sigma. So with the hierarchical model, we can convey the fact that there's measurement noise associated with each condition for each person. And I've shown you code where we just have common measurement noise across conditions and across people. I think I also showed you code where each person got their own sort of value for measurement noise. And today I'm going to show you how you can actually just allow measurement noise to vary even across conditions within the same person. So in effect, we're going to say that there's an intercept for a given person's mean reaction time, and there's an intercept for, and there's an effect for that person's mean reaction time. We'll also say that there's an intercept for that person's measurement noise and an effect of whatever variable this is on measurement noise. So just like the mean is something that can be influenced by your predictor variables, the amount of measurement noise can be something that can be influenced by your predictor variables. That tends to, well, there's some scenarios where that's actually known to happen, that the change between conditions actually manifests not only in a change between means, but also in a change in the measurement error. Certainly, having this bit, that each person has slightly different measurement noise from one person to another, is a really useful addition to a model, and that people actually do tend to differ from one to another in the amount of measurement noise. And if you have something like an experiment like this where it's reaction time and you are measuring people across a wide range of ages, you're going to tend to find that people sort of in the peak cognitive performance realm are going to have very low measurement noise. So in the 20s and 30s, as you get younger and older, they're going to start to have more measurement noise. So having measurement noise able to vary from person to person, or if you want to add in age as a predictor and therefore having age have an effect on measurement noise, can soak up a lot of error and therefore give you better precision for your inferences on the other things you're actually interested in. You might even be interested in the degree to which measurement noise is affected by your predictors. So we're going to have a model where we not only have the error rate things, we're going to have effects on the reaction time mean, and also effects on reaction time noise. So I have this already coded up in today's folder, bivariate error RT. So I'll open up that project. And I made a dummy data set. Let's see, where is it? Example.r is where it's set. So we'll load in everything we typically do. I'll make that a little smaller for today. So there's a data set called the ANT made available by the package called Easy. It's actually a made-up data set, but it's got this structure where it has, make this wider. It has a bunch of people, subjects. It's got a between subject variable here. It's got 2 within subject variables. It's got a couple other within subject variables that I'll ignore for today. And it has a reaction time and error for each trial that's in the data set. And there's a bunch of trials within each combination of person and the within subject conditions. Now, if you actually look at this data set, I'll say with ant table q flank, it's actually like a 4x3 design. For today's purposes, I actually am going to reduce it just to a 2x2 because that'll be easier to look at. But this general procedure will work for a 4x3 design, as I've shown you in the past for all our stuff. So in terms of preparing the data for STAN, it's identical to what we've covered in the past for mixed hierarchical models. Regardless of if it's binomial or not, you generate your within subjects contrast matrix. So we've got an intercept, effective Q, effective flank, and an interaction between Q and flank. You narrow down to just one observation per person and get the between subjects contrast matrix. Here we only have one between subjects thing. It's called group. Package the data up for STAN, and I'll step through this one. Usually we actually we sort of supply just an argument to the call to STAN, but I'm doing this, I guess, beforehand because this is a very long thing to put all inside the call to STAN. So creating an object called data for STAN, which is the list with named elements and trials. It's the number of rows in the original data set. How many observations did you make? It's expecting something to come in called reaction time. I didn't bother to create all the scaling that we typically do with a Gaussian variable inside the STAN file. So I scale it outside. It needs something coming in. It wants to know the errors, I guess the labels for each trial, whether it was an error or not. And that's just coded in this column called error. 0 for no error, 1 for yes, there's an error. One thing that's a nuance to the world of when you're doing reaction time research and you're interested in the degree to which a variable affects either reaction time or error rate is whenever you look at the reaction times, usually you're only interested in when they got it correct. So you have to, this is ACInd, it's just the indices of the accurate trials. So like for every number that there are for trials, this is just a list numbering the accurate trials. So if trials 1 and 2 were accurate, this would have 1 and 2. If 3 was inaccurate, it would skip 3. If 4 was accurate, it would say 1, 2, 4, etc. So it's just getting the indices within this list of reaction times for those reaction times that actually are accurate. NS, number of subjects. So we get the number of unique subjects in the subject label column. And S is supposed to be just the subject for each trial. So we use our trick to convert to a factor and then a number to ensure that the labels we're passing in are ordered from 1 through to the number of subjects there are. And then sort of some differences from what you've seen before. Before we used to say how many within subjects predictors there are and how many between subjects predictors there were. Now we actually are telling it how many within subject predictors there are on the error rate, how many between subjects predictors there are on the error rate, and ditto for how many within subjects predictors there are on the mean RT and how many between subjects predictors there are on the mean RT. And finally, how many within subjects predictors there are on the standard deviation or noise, the standard deviation of RT, and how many between subjects predictors there are, standard deviation of RT. Now, if you notice, they're actually all just the same. That's because I'm going with what you might call the full model, where for every outcome, error, mean RT, and standard deviation of RT, I'm just giving it the full model matrix so that if you wanted to, for example, reduce the model so that you only wanted to have subjects differ from one another, an intercept effect on the standard deviation of RT, but no like Q effect or flank effect, you can give it a reduced predictor matrix and it will handle that. So I made it flexible enough to handle if you just wanted a subset of the predictors to influence each outcome. And of course, after giving it the length of each of these matrices, I actually give it these matrices as named things. Now, again, I'm just giving it W and B for each one. So I'm going to open up that hierarchical.stan, show you a little bit of what's inside of it. Again, we're getting into more complicated models here where I'm kind of more trying to pique your interest. I'll try to show you the internals to the degree that I think it would be not a waste of your time, i.e. that show you the things that would be somewhat familiar to you. So beyond the data declarations, it computes out like what is the total number of within subject predictors. So it just sums up the number of predictors on error rate, the number of predictors on RT, on mean RT, and the number of predictors on standard deviation of RT. Because it's going to compute it's going to create the coefficients as one big matrix in order to establish correlations between predictors' effects on different variables, error rate and mean RT and standard deviation of RT. It also, as like a quick trick to get a good intercept to set the prior properly for the error rate, the intercept on the error rate, it actually computes what the mean error rate is in the data, and then log odds transforms that. So that way we can, again, apply a fairly default prior to error rates. I've been giving you guys default priors that are really wide on error rates. So it's a normal on log odds scale with a 4 usually, or maybe even up to a 10 uncertainty. That can, particularly with much larger models, that can get you into some trouble by being so uncertain about the effects of things. So this applies a trick of saying, okay, center the intercept at whatever the original intercept of the data is. So it's very similar to what we're doing with scaling the RT data, and then the intercept becomes the prior that we set on the intercept of normal 0, 1 ends up being centered on the intercept. But we're not that interested in that intercept. Ditto with the error rate intercept. We're not super interested, but we still want to convey some uncertainty on it. So that's why that's there. The internals for the parameters should be somewhat familiar to you in that last class I showed you a faster thing that had similarly named variables. So there's a dummy variable where we're sampling from a normal distribution that I won't tell you about. There's the thing that we're expecting, which is for every within subject predictor, there's a variability across people in that within subjects predictor's effect. So we have standard deviations associated with each of those. We've got a big correlation matrix, as big as the number of items that we have. And then we have coefficients for each outcome that will get filled in the model section. Model section, I won't go into this. It's an extension of the HNG Factor that you guys had the other day, with the exception that it computes out this big thing here, which is subjects' deviations on all of the within subjects things, and then works out for each outcome the grabs, so the first bunch of predictors are associated with the error rate, the second bunch of predictors is associated with the mean RT, and the last bunch of predictors is associated with the standard deviation, the noise parameter. So then it just works out for each row in the data, what the prediction for, given that person and given the contrasts for that row, what the prediction for the outcome should be on error rate, what the prediction for the mean RT should be, and what the prediction for the standard deviation of RT should be. And these last two lines where it says target plus equals, you might see this in a lot of stand code that's out there. This is equivalent to saying, so when it says target plus equals Bernoulli logit LPMF, that's equivalent to saying ER is distributed as Bernoulli logit. So these two lines are equivalent to Stan. In this particular case, I happened to decide to use one over the other. Partly actually to show you guys that you'll sometimes see this, or to remind me to give you guys a heads up that sometimes you'll see this other. So for example, this line, so I'll put a comment. And I'll put a comment under this. So be this. This. So, now one thing to note, does anybody remember why, so again, this expression is saying the same as this thing down here, so we've got normal distribution with a mean indicated by this thing. And here, I'll take off the comment. Oops, so the coloring is nice. And what's this over here?
That has something to do with it being on the log scale.
Okay, on the log.
Just
so,
log.
Yeah, so this is the noise thing. And noise can't be less than 0. So a common solution to still modeling that there's an intercept plus an effect without having to then make sure that that combination of intercept and effect always come out as positive is to model an intercept and effect on the log scale, so that to get the actual unlog scale, you exponentiate it. So that's a common solution to that. And it's pretty, there's actually some good mathematical reasons to expect that to the degree that there's variability from one person and another on something like a noise parameter, it should probably be log distributed, log normally distributed. So, yeah. The final last little bit is to get out what the correlation matrix is, given this helper thing that we used up above that I didn't really tell you much about. So, given a model like that, you can give it its data, you can sample the posterior. I've actually already done that. It takes well, for this data set, it only takes a couple minutes. Load post.our-data. So that should load everything in as if I sampled it right here now. Actually, I am going to show you a little bit here. Have I shown you this bit yet? If you've got a big model like this, and in this model, there's a bunch of things that I actually don't care about. I actually didn't. Well, one of the things is like this dummy variable that I used. I don't actually want to save that. I also don't want to save this course helper thing, because later on I only use that to figure out what the correlation matrix is down here. So I don't want those two variables in my output. It can take up space if you've got like a really big model and lots of iterations, so especially if I want to save it later. So to tell it the names of things that you don't want to keep, you can use the parse argument to stan. So you just give the names of variables in the model that you don't want to keep. And to explicitly say, don't keep these ones, you say include equals false. Otherwise, if you said include equals true, which is the default, it would only keep these ones. So you can turn it from a list of things to keep to a list of things to toss by saying include equals false.
So does that mean that it's using it in the model, but
Yes,
it doesn't return it?
But it's not
for you?
saving a record of those values. So I want to look at the coefficients associated with the effect of our within and between variables on error rate. And again, this is a binomial model, so it's on the log odds scale. And this is what gets spit out by Stan's summary. These numbers, again, log odds. So the intercept, of course, is really low. That corresponds to, let's see, p logis 0.2, negative 2.4-ish. So about an 8% error rate overall. That should correspond to what you actually get if you compute just the observed mean. And just by looking at the credible intervals, none of these variables seem to affect error rate. That's actually really rare in reaction time research and is only a product of the fact that this is fake data. And I didn't, at the time that I created this fake data, think to add in effects on error rate. But obviously, if you're not using the fake data, you want to look at error rate as like an outcome in this sort of data. So in the same way that we looked at the coefficients effects on error rate, we can also look at the coefficients on mean RT. And here we will have some effects. Now this is on the scaled because I didn't bother to include the scaling inside the model. So way up here when we created the data for Stan, we gave it scaled RT. So if I wanted to get out like what the real intercept was, I'd need to multiply by the standard deviation of this column and add in the mean of this column. I'm not going to bother for just telling you guys about it today, but you can see that there's, well, of course, the intercept on the Z scale is going to be pretty much centered on 0, and there's some effects, i.e. the 95% credible interval excludes 0 for a few of these things, including this three-way, which would be a headache to actually interpret. But finally, we also included in the model the ability for the different variables to affect the amount of noise that manifests. So we can take a look at that. There's an intercept, which should be non-zero. But otherwise, there's a bunch of, oh no, the intercept, these are all still on the log scale, so it could be 0 or it could even be negative as it shows here. So yeah, so there's an intercept, but not any effects of our predictor variables on noise, because again, at the time that I generated this data, there actually wasn't, I didn't think to add that in. Could look at the correlations. There's a lot of them because there's in each of these matrices in W and call W. So it's a 4 plus 4 plus 4. It's a 12 by 12 matrix. Oh, right, because it actually even just shows us the whole 12 there. Oh, I didn't say is core here. Is core equals true. Yeah, it would. That shortens the list here because it actually only gives us the upper triangle. Otherwise, it gives us the full matrix, which is redundant. It shortens the list, but it's still a really big correlation matrix. You can kind of just glance through again, and the 95% credible interval for all of them are thoroughly centered on 0. So it's not, and again, that's because I didn't add any correlation to this fake data.
So that's, you get 6 correlations for each outcome, right? 6 for error, 6 for
Well, if you remember, all the outcomes can actually intercorrelate. So you'll get 4 correlations per outcome, because there's it's a 2x2 model for each outcome. Intercept, main effective Q, main effective flank, interaction between Q and flank. So instead of one thing here, it would be 4 things for each outcome, and then the intercorrelations amongst the outcomes. So that ends up being 12. Yeah. So I mean, this data set's kind of boring in the in what it actually has as results, but that's the kind of thing that you can do, and I guess you can take it from me that in this realm of reaction time and error rates, it can be very beneficial to like your statistical power and your ability to accurately detect things and see correlations if you actually include all the data in the same model. Yeah. But I'm going to save that. That's all I wanted to talk about today. I thought I'd leave the rest of basically almost every classroom here on in to, if anybody wants to stick around and actually work on their project while I'm here, we can do that.